Mesophilic versus Thermophilic Anaerobic Digestion for food waste, the definitive expert verdict. Food waste is a massive energy resource, but how we process it matters. The debate often comes down to mesophilic versus thermophilic digestion. What if simply turning up the heat could increase your methane yield by over 22%? This high-temperature process also works much faster, cutting treatment time by nearly half in some cases. Faster processing means you need a smaller, less expensive reactor, potentially reducing the required volume by 40%. More gas, faster processing, smaller footprint. The case seems closed. But the reality is far more complex. We'll break down the hidden risks to find the answer. Let's quantify the thermophilic advantage. First, organic loading rate. These systems handle higher concentrations of food waste. The high heat is incredibly effective at killing pathogens, achieving up to 99.9% elimination of E. coli. This sanitation level means the digestate can qualify as Class A biosolids, a valuable fertilizer with fewer restrictions. With all these advantages, why isn't every plant thermophilic? The answer lies in one critical word: stability. Mesophilic systems, operating at moderate temperatures, are the industry workhorses. They are famously dependable and far less sensitive to change. This stability makes them more forgiving, reducing the risk of process failure. It's why mesophilic remains the most mature and widely used technology. Let's look at the physics. Maintaining a reactor at 55 degrees Celsius requires significantly more energy than holding it at 35 degrees. But the fragility of thermophilic systems isn't just about temperature swings. There's a chemical vulnerability. So what's the hidden enemy inside a hot digester? The enemy is ammonia. At higher temperatures, more ammonia converts into its free, toxic form, poisoning the microbes producing the methane. Alongside ammonia, there's the risk of rapid acidification from volatile fatty acids. Mesophilic systems handle these swings better, preventing a system crash. This stability difference comes down to the microbial communities. Mesophilic digesters host a diverse, resilient ecosystem. Thermophilic digesters are specialists, efficient but vulnerable. We've established the core conflict: high performance versus high reliability. How does this play out in terms of overall system economics? We said thermophilic uses more energy for heating. That's true moment to moment. But the complete story is different. And the economic wins continue after digestion. Thermophilic digestate is often easier to dewater, reducing biosolids handling costs. The choice is getting tougher. The economic case is stronger than it appears, but the stability risk remains. So, can we get the best of both worlds? Modern plants rarely use one solution in isolation. Let's look at process optimizations. First, co-digestion. Mixing food waste with materials like sewage sludge can balance nutrients and buffer against ammonia, making either system more stable. Second, pre-treatment. Methods like thermal hydrolysis break down waste before digestion, boosting methane yield for any temperature you choose. These methods help, but they don't solve the fundamental trade-off. What if you didn't have to choose between a fast system and a stable one? Recall thermophilic strength, rapid breakdown of organics, and mesophilic's stable methane production. The most advanced systems combine them. Enter temperature-phased anaerobic digestion, or TPAD. It's a two-stage process designed to use the best of both temperature regimes. Here's how it works. Stage 1 is a thermophilic reactor for rapid breakdown and pathogen kill. The output then flows to Stage 2, a mesophilic reactor for stable methane conversion. The result? You get the speed of thermophilic with the stability of mesophilic. This hybrid can increase methane yield by over 50% compared to a single-stage system. So, after examining performance, risks, and hybrid solutions, what is the final verdict? There is no single better system. The optimal choice depends on project goals. For maximum pathogen kill with high operational expertise, thermophilic is a powerful choice. For simplicity, unmatched stability, and lower capital costs, especially with variable feedstock, Mesophilic remains the proven, dependable standard. But for facilities seeking the absolute highest performance without compromising stability, hybrid systems like TPAD represent the future of food waste digestion. The final decision rests with the engineer. By weighing feedstock consistency, energy costs, and operational capacity, you can design the system that creates the most value. Thanks for watching, and our resource link can be found in the description.